Hello everyone, welcome to DT Studio. So let us start discussing on basics of electrical and electronics engineering curriculum framed for first year diploma ENC students. Myself Megha from ENC department of Government Polytechnic, Belagavi. Let's look at the references I have referred to prepare today's content. Quickly, let us have a short recap of previous session content. So last class, we have discussed about AC circuits analysis, considering R, L, and C, that is resistance, inductance, and capacitance in series. So under that, we have tried to understand what is the effective voltage, and also we have tried to derive the expression for circuit current. Other than that, the total opposition offered by resistance, inductance, and capacitance, which is termed as impedance, is given by square root of R square XL minus XC square. XL and XC are the reactances or the oppositions offered by the inductor and capacitor respectively. With respect to the phasor diagram, as we can see here, we have a phase difference between the current and voltage by measured as phi, and we can calculate this phi considering the impedance triangle, where phi will be equal to tan inverse of reactance by resistance. Other than that, we have also seen what is the power consumed by series RLC circuit, which is given by VI cos phi, and the expression for circuit current can be expressed I is equal to Im sine of omega t minus or plus phi, given applied voltage is V is equal to Vm sine omega t. So friends, enough time was spent deriving the expressions, analyzing the phasor diagrams, and also the series circuit. Other than this, we have gone through the case studies along with the simulations on multisim. When the inductive reactance is more than the capacitive reactance, you have a phase or current lagging the voltage, where the phase is positive, circuit behaves like an inductive circuit. And the second case, when XL is less than XC, the network is capacitive, phase will lead, or I think current leads the voltage. The phase, whatever angle we have, it will be negative. That is, it falls in the fourth quadrant. Coming to the last case, when both the reactances are equal, then the circuit is pure resistive and the phase angle is exactly equal to 0. The current and phase are aligned along the same direction. Other than this, we have gone through the little bit math part of AC quantities. That is, any AC quantity, as we have seen, can be represented with the help of phasors. These phasors are nothing but the vectors, and we have some four standard representation for the vectors, namely rectangular form, polar form, exponential form, and trigonometrical form. So we have in detail dealt about the each representation, the rectangular form, which is in the form of A plus JB, polar form, which is R theta, and exponential, which is X e to the power J theta, and trigonometric R cos theta plus J sin theta. We have also discussed how to convert from one form to another. So other than this, manipulation on these AC quantities, that is, when you represent in any one among these four, you can add, subtract, multiply, divide the AC quantities easily. Whenever it is a matter of addition and subtraction of AC quantities, rectangular form is more convenient. And whenever it is multiplication or division, polar form is more convenient. So when we need to add or subtract, we just need to add and subtract real terms and as well as imaginary terms. Similarly, on the other side, multiplication and division, magnitudes, whenever you need to multiply two AC quantities, just multiply the magnitude part and add the phases. When it is a division, then divide the magnitudes, subtract the phases. The complete table representing all the 6 combinations of the AC circuits when it is connected to a pure resistance, pure inductance, pure capacitance, or R and L when they are connected in series, R and C when they are put up in series, or you have all the 3. resistance, inductance, and capacitance in series, what is the polar representation, rectangular representation, what will be the phase angle, power factor, and also whether we have a lag or lead between the voltage and current. So friends, I think if you just remember this table, then it is sufficient to recap all the AC circuit analysis with the 6 combinations whatever we have discussed in the 4th chapter, that is AC circuits. Now let us proceed towards the next unit, which is electrical machines. So electrical machines, we are supposed to know what are static and dynamic type of machines. In that, a particular detailed study about the transformers, which are an example of static type of machine. So under transformer, we need to know its operating principle, EMF equations, voltage transformation ratios, and different types of transformers with losses, efficiency, and regulation. So classification of transformer, you have a wide classification depending on the application, depending on the power, depending on frequency. You have different types of transformers. And then specific application oriented auto transformers, isolation transformers, and pulse transformers. Other than this was in detail discussion about the transformer, which is a static machine. We have a dynamic machines called as DC machines and AC machines. So we need to understand what is the working principle of these features and applicability. Simple problems associated with each concept as and when required, we can go through it. So let us begin with basic definition of what is an electrical machine. So these electrical machines are nothing but which are associated with the electricity at both input output, or it can be only at the input side or output side. Hence, we can define these machines which are electrical or can be called as electric machines are operated in relation with the electrical energy. Yes, so we have the input or the output, or both input and output can be electricity. So all type of machines, they generate the electricity by either converting mechanical energy into electrical energy, or they do some work or they perform some task by converting electrical energy to mechanical energy. Hence, the definition of electrical machine is a device which converts mechanical energy to electrical energy or vice versa. So friends, you might have encountered with such type of machines in your day-to-day life. Maybe it is a sieving machine or the motors, different types of generators. So these are all examples for electrical machines. Now let us have a quick review of the classification of the electrical machines. Broadly, electrical machines are classified as static and dynamic. So dynamic type of machines are also called as rotating type of machines. The machines which are static will be an example like transformers. And coming to dynamic type of machines, they can be further classified into 2 types. Either they can be DC machines or they can be AC machines. DC machines can further be classified as a DC generator or a DC motor. Under the category of AC machines, you can have a synchronous type or an asynchronous type of AC machine. Under the category of synchronous machine, there can be a generator. It can be a generator which will be basically generating an AC signal from a mechanical input or mechanical energy, or it can be a motor where it will be converting an electrical energy, which is an AC, into some mechanical energy. So these synchronous generators can be 1 phase or 3 phase, or even the 3 synchronous motors can also be of 1 phase, 3 phase. The asynchronous machine are the induction machines. These can also be of 1 phase or 3 phase. So friends, the broad classification of electrical machines I think is clear. Basic electrical machines can be of two types, that is static and dynamic. So let us look into the details of static and dynamic machines. So static machines, the name itself indicates something which is stagnant, or you can tell these have only the stationary parts but not any rotating parts, or even these doesn't rotate while they are working. So such type of electrical machines will be termed as static machines. And the best example to code for static machine will be a transformer. So an basic small transformer has been shown here. So next category is dynamic machines or the rotating type of machines. These have stationary parts as well as the rotating parts, and these do rotate when they are working. So the examples for dynamic machines is generators and motors. So as you can see some images, so this is an DC motor, you have a AC motor, you have a stepper motor, so induction motors. So these are all examples for dynamic machine where they have some rotating parts within themselves. So they do rotate or make movements while working, hence the name dynamic machines. So let's now go into the specific electrical machine, which is called as a transformer. As we have seen previously, the transformers are the examples for static or stationary type of machines. Hence, these transformers can be defined as a piece of apparatus or a static piece of apparatus by which the electrical power in one circuit is transformed to the electric power to the other circuit, maintaining same frequency. It means that the input signal and the output signal have the same frequency, but there is a variation in electric power. That means you have a different input voltage and current, and you have a different output voltage and current. But the frequency at the input and the output are same in case of transformer. And these are the devices which work on the principle of mutual induction. That is, when the two circuits are linked or they are connected by magnetic flux. You can see a small example for a transformer. So you have something called as a laminated section in this device, which is called as core, and there is some winding or a coil wound on the one leg of the core, and you have one more winding around the other leg of the core. So this is a example, or this is a simple general purpose electrical transformer. Let's look into more details of this transformer. Let us try to analyze the transformer. So these transformers are basically transforming the energy from one circuit to the other circuit by the principle of mutual induction. So friends, just look here. You have a material, or you have a core which is owned by two coils. You have a blue colored and an yellow colored coil showing here. So you can see the movement of the carriers through these coils. Now though you don't have any energy fed to the secondary coil or the second coil which is shown here, but still we have the movement of carriers, or we have the flow of current in this coil through the principle of induction. So the source which is connected to the primary will be responsible for the flow of current in this coil through the flux. So the magnetic flux which is spread around this coil will try to link to the other coil which is connected through some steel or a uh, metal body. So this coil, which is termed as the secondary coil in this case, is induced, or it is getting an EMF induced due to the current flow in the primary coil. So as you can see here, the movement of carriers, which is corresponding to the flow of current in both primary and secondary. So the amount or the magnitude of the current flowing in the secondary coil is dependent on the voltage which has been connected to the primary, and also the number of turns present in the secondary. So you can see here there is a difference in number of turns of the coil which are put on the each leg of the core. So to summarize, transformer is a device which transfers the power from one circuit to the other circuit. So previously, as you can see, as you have seen in the video, the primary winding of the coil can be connected to one circuit, and the secondary winding of a coil can be connected to the other circuit. So both the circuits are completely isolated, but there is a flow of current, or there is a flow of energy from one circuit to the other circuit through this transformer. So these transformers do this job without any change of frequency. So you observe no change in the frequency, but the working principle is based on electromagnetic induction, and these two electric circuits are actually connected, or they are linked by mutual induction. So you can see some images here. These images are transformers where you have a core type and a shell type as mentioned. So these are different from the constructional point of view. So next session we will be looking into more details about the classification of transformers based on construction, application, losses, etc. So this is an example for one phase core type of transformer. Whereas look at the other figure, it is an example for core type only because each leg of the core is connected with a different winding. So each leg of a core is connected with a different winding. Hence, but you have this three-phase transformer. You have three-phase transformer. And whereas shell type, you can see the difference. Shell type, the winding is present on the center leg of the laminated core. This is an example for one phase, and this image is an example for three-phase shell type transformer. So the same has been put up here to make you understand what is the difference between core type and what is the difference between shell type. Now let us understand the working principle of a transformer. So if you try to look at the basic transformer, as you can see here, it is a core, laminated core with two windings on legs of the core. So this is a general purpose transformer. So transformer is called as a static machine because you don't have any rotating parts involved, and this device is not moving while it is working. So it is an example for static machine as we have seen. You can observe there are two windings which are around the legs of the core. These windings can be thought of as two inductor coils. And other than this, you have an important element present in the transformer, which is called as core. So the core is shown here. So it is an example for core type of transformer. So now if we can think of the coil which is wound around the leg of the transformer as a simple inductor. Now if you try to connect an alternating source, voltage source, to the ends of this inductor, then we have a flux associated with this coil. When the voltage connected is of alternating type, that is varying, then even the flux surrounding, that is inside or outside the coil or the winding, also changes or also varies. This changing flux will produce a current flow through the coil, and also the current is proportional to the flux. The alternating voltage, which is responsible for the change of flux, is now responsible for current flow through the coil. Now, to know the directions for the flow of current as well as the flux, we can apply right hand grip rule. So if you try to apply right hand grip rule, where the thumb is aligned along the axis of the coil and the fingers towards the turns of the coil, then we get the direction of flux. We get the direction of flux along the thumb, that is as shown here. So you can observe if the fingers of the coil represent the direction for current, if the fingers represent, if the fingers of your right hand represent the direction for current, and if thumb is aligned along the axis of the coil, then always the thumb direction will give us the direction of flux. Yes, now we have got the direction of flux as well as direction of current using right hand grip rule. Now if you try to plot the behavior of the flux and as well as current, then we have the variation of the flux in correspondence to the variation in the current. So we have a maximum flux at the point where we have a maximum current too. So it is increasing since the applied voltage to the coil is alternating type, particularly a sinusoidal type of alternating quantity. Then you have even the flux variation also to be sinusoidal. And then that is resulting in also the current variation. Now you have a maximum flux which will correspond to the maximum flow of current through the coil. When the flux is becoming exactly equal to 0, then even the current flowing through also is 0. So after that, you have a flux in the opposite direction or in the different direction. It is reaching a peak in the opposite direction also, which is even resulting in the negative or different direction for the current. So hence we can uh, observe here that you have alternating directions for flux as well as current in correspondence to the supplied voltage. So the peak values correspond to the maximum flux and maximum current value. Now if you try to look at the coil what we have considered, where the supply voltage alternating type is connected, then the electric flux produced is shown here. Okay, alternating current produces alternating flux. Now, till now, we have analyzed that only one coil, considering only one coil which is on the one leg of the core. Now, but we have one more coil put up on the other leg of the core. Then you have, due to the flux variation and current flow, you have EMF induced in this coil, which is exactly equal to the supplied voltage. And due to the mutual induction, okay, due to the mutual induction, you have even an EMF induced in the secondary winding of the coil or the second coil which is wound around the core. Now, according to Faraday's law, EMF is directly proportional to the rate of change of flux. Now, to understand the EMF induced in this coil will be directly proportional to the rate of change of flux. Now, if you want to know what is the EMF induced in this coil due to the first coil, then we can connect a load across the secondary or the second coil and try to measure the voltage across that load. So there is a current flow in this coil which is in proportionate, or it is depending on basically the supplied voltage which is connected to the first coil. Now if you have a setup like this where a supply voltage is connected to the primary winding and you have a load across the secondary winding, then the rate of change of flux, if phi represents the magnetic flux, then you can write the rate of change of flux as d phi by dt. Now, EMF induced, or EMF available at the first coil is exactly equal to the supplied voltage. So since the supply voltage or the source is connected to one end of the coil, we can call this winding or this coil as primary winding, and say you have an EMF induced due to self induction due to the supply voltage as say E1, and this primary winding is having N1 number of turns. N1 number of turns. Now coming to the secondary coil, if the secondary coil has number of turns equal to N2, so due to self-induced EMF V1 across the primary winding, and you have the current flow due to the flux in this coil into the core, and that is linked to the other coil which is connected to the core, and that current will try, or that change of flux is responsible to induce an EMF in the secondary. So now if you want to calculate what is the EMF per turn in the primary, that will be equal to the total voltage V1 by the number of turns present in the coil. That is equal to V1 by N1. Now similarly, we can see here if N2 is the number of turns for the secondary coil, and if the voltage V2 is induced across the secondary, or the voltage absorbed across this load is V2, then the input given to the each turn of the coil will be equal to V1 by N1. And if you multiply that by the total number of turns which are present in the secondary, that is N2 V1 by N1 will be exactly equal to the voltage drop available across the load which is connected to the secondary winding. Since the load is always connected to the second coil which you have here, this type of winding present is called as secondary winding. So the one which is connected to the source or supply is called primary winding, and the one which is connected to a load is called as a secondary winding. So that now the total EMF available across the secondary will be the input or the EMF induced into this due to primary, that will be V1 by N1. If you multiply that by N2, we'll get the total voltage V2. Now, if you have these number of turns on the primary winding and secondary winding not equal, okay, if you have a difference in number of turns on the primary and secondary, then the EMF induced in the secondary and in the primary will also be different. They will not be equal. So when N1 is not equal to N2, then even V1 will not be equal to V2 because they are proportionate. Or else we can now check if N1 is less than N2, that is number of turns in the secondary winding are more than the number of turns in the primary winding, then in that case the voltage available at the secondary winding will be more than the voltage applied at the primary winding, and such type of transformers will be called as step up transformers. Friends, I will repeat, if the number of turns in the secondary winding are more than the number of turns in the primary winding, then you observe the voltage or the EMF across the secondary winding to be greater than the voltage applied at the primary winding, and such type of transformers are called as step-up transformers. Similarly, if you have the number of turns, now in this example or in this image, obviously we can make out N1 is greater than N2. That is, number of turns in the primary is greater than the number of turns in the secondary. So in that case, the supply voltage or V1 is greater than the voltage available across the secondary or the load. So such type of transformers will be an example for step down transformers. The name itself indicates step up corresponds to something boost or increase in the level, whereas step down corresponds to decrease or buck type of signal. So here, when it is a step up transformer, the secondary winding has an voltage greater than the primary winding. And when it is a step down transformer, the primary winding has a voltage greater than the secondary winding. So this was a brief introduction for the understanding of transformer. Now let us proceed towards the EMF equation for a transformer. So as we have seen, when an alternating voltage which is connected as a supply is of sinusoidal nature, one cycle, okay, considering one cycle, we can draw the flux or flux variation associated with the coil. So it will be also sinusoidal. So the variation is proportionate to the supply voltage what we have connected. Now the maximum flux reached during the positive alteration will be say phi m, and that is at exactly, and that is exactly, friends, look here, this is one cycle I have considered. So this is corresponding to time period t, and this will be t by 2. So if you consider the duration for maximum flux, it occurs at exactly t by 4 seconds time. Now if we consider n1 to be the number of turns in the primary and n2 as the number of turns in secondary, then the maximum flux, okay, the maximum flux linked in the core or available in the core, if you represent in Webers, it will be given by magnetic field multiplied by the area. So that I have taken Bm multiplied by A. Now if F represents the frequency of the applied AC input in hertz, then what is the average rate of change of flux? So if you want to calculate first change of flux, so change of flux, if we consider the quarter cycle, so the change of flux is from 0 to phi m. So if you write the change of flux, it will be phi m minus 0. Or if you want to calculate the average, then divide by the base, that is t by 4. If I try to represent the t in terms of frequency, then I can write it to be phi m by t is 1 by f. So you get 1 by 4f. So I hope this term is clear with you. Phi m represents the change of flux in quarter time period, and the time base, which is in terms of frequency, is written here. So it will be Webers per second. Flux, rate of change of flux will be Webers per second. Now we know what is the EMF induced per turn. Okay, it will be equal to, yes, this is exactly equal. The rate of change of flux we have seen from the video, the rate of change of flux is exactly equal to the EMF induced per turn in the coil. So that is exactly equal to 4 multiplied by phi m multiplied by f volts. Now if flux phi is a variation sinusoidal, then RMS value of induced EMF, we have seen the definition form factor in the previous chapter, which is equal to RMS value by the average value. So we can always calculate now RMS value if we know the form factor multiplied by the average EMF per turn. So form factor for a specific sinusoidal, we have already done it in the previous class. So it is equal to 1.11 for sinusoidal. So form factor multiplied by the average. So we have found the average uh, value for the EMF is 4f phi m volts. So when you multiply 1.11 by 4, we get 4.44 constant multiplied by frequency and maximum flux. Hence, the RMS value of induced EMF per turn is this much. 4.44 multiplied by frequency multiplied by maximum flux. Now, if you want to know the complete primary winding EMF, then you need to multiply it by number of turns. So if you multiply by the primary winding turns, we will get the EMF induced in the primary as E1, which will be equal to 4.44 multiplied by F multiplied by phi m, and this is N1 corresponding to the, as you can see, the primary winding. If it is having N1 turns, then multiply that by N1, we will get the expression 4.44 F Im N1. Or if you want to represent in terms of field, then you can write it Ba. Similarly, we can even write the expression for EMF in the secondary winding, which will be equal to 4.44 F phi m. And now you need to multiply by the number of turns which are present in the secondary winding. So if N2 represents the number of turns in the secondary winding, then we can write 4.44 F multiplied by N2. So ideally, with no losses, with ideal zero losses in the core or no losses in the transformer, we have V1 should be equal to E1 and E2 should be equal to V2. So you can see here, V1 is nothing but the supply voltage which is connected to the primary winding of the transformer. And due to this self-induction, you have an EMF E1 induced in the primary. So when there are no losses, then these should be exactly equal. Similarly, when you have an EMF E2 induced in the second or the secondary winding due to mutual induction, then this E2 should be equal to V2. That is, whatever you have the voltage drop across the load, that will be equal to the EMF induced in the secondary winding. Now, I hope the EMF equation for the transformer is clear. Now, let us proceed towards the voltage transformation ratio. We have seen ideally V1 should be equal to E1 and E2 should be equal to V2. Then if you take the ratio E2 by E1, that should be equal to V2 by V1. And that is dependent on what? It is dependent on the number of turns which are present in the primary and secondary, and which is called as a voltage transformation ratio. So voltage transformation ratio, which is nothing but K, is either defined as the ratio of number of turns, or in terms of the voltages, or in terms of the induced EMFs. Now the case, as we have seen, when the secondary has more number of turns with respect to primary, then obviously the K value will be greater than 1 and it will be called as a step up type of transformer. When the secondary winding has less turns compared to primary, the value of K will be less than 1 and it will be a step down transformer. For an ideal transformer, you have input voltage current exactly equal to output voltage current. That is, power at the input should be equal to the power at the output. Or you can even write volt ampere as V1 I1 is equal to V2 I2. What is V1? V1 is nothing but the supply voltage applied to the primary, and I1 is the current which is flowing in the primary. I2 is the current flowing in the secondary winding, and V2 is the voltage available across the secondary winding. Now I2 by I1, expression for current, I2 by I1 will be equal to V1 by V2, which is the reciprocal of the voltage transformation ratio, that is 1 by K, reciprocal of voltage transformation ratio. So this is regarding voltage transformation ratio. We can take some simple problems associated. So friends, I think the EMF equation of a transformer and also the transformation ratio with respect to voltage, with respect to number of turns is clear. We can now take some simple problems like 50 kilovolt ampere transformer has 500 turns on the primary and 100 turns on the secondary winding. If the primary is connected to 1000 volts, then calculate the secondary EMF, primary and secondary currents. So let us first write the given data. The number of turns on the primary is given, which is equal to 500, and the number of turns on the secondary is also given, which is equal to 100. Correct? So 100. Then now primary is connected. So this is the voltage 1000. Ideally, E1 is equal to V1. So we can write E1 as 1000 volts. And it is a transformer of rating 50 kilovolt amperes. We are asked secondary EMF E2, primary and secondary currents, that is I1 and I2. As we all know, the voltage ratio, transformation ratio, E1 by E2 is equal to N1 by N2. Since we know the value for N1, N2 and E1, just try to substitute here. So we get 1000, which is equal to E1 divided by E2 is equal to N1 500 by 100. So we get E2 is equal to exactly 200 volts. Similarly, if you want to know the current I1, we know the power voltage, that is voltage current ratings VA upon E1. What is VA? VA is mentioned as 50 kilo. So it is 50 into 1000. Kilo is a prefix which stands to 10 to the power 3. So 50 into 10 to the power 3 divided by what is E1? E1 is mentioned as 1000. So E1 is substituted. We get a current for I1, that is primary current, 50 amperes. Similarly, we can calculate the secondary current also, which is VA. Ideally, both are equal, input and output. Hence, VA by E2. Sorry, make a correction here. It should be E2. It's just written typo error. So VA by E2. So we get 50,000 upon what is E2. We have found it to be 200. So substitute 200 here. We get secondary current of 250 amperes. So I hope the solution is clear.